Okay, welcome everybody, and this is our first opportunity to be on the road, and we're really delighted to be down here in D.C., our nation's capital. A lot of things happening in politics, so at least it's died down enough that we can get another story out besides political story regarding election. So I'm going to be taking you through some fundamentals and introducing you to our sun cell, which we have a this is exactly what the sun cell, this is an exact model. It's not a replica, it's actually a model identical to what we run in the video I'm going to show you in terms of it operating. And I'm going to go through the different mechanisms and the chemistry, and even more fundamental is I'm going to give the timeline of the inception through to the creation of that device. So this is kind of the first time I've run through that. And so we'll talk more about going to market after that, and what opportunities there are in the market. And as you can imagine, they're absolutely phenomenal market opportunity. There's like we're talking biblical, proverbial opportunity. So just fundamentally, what we've devised is a new form of primary energy that can replace all forms of power on the planet. That's now an economic foundation for climate change and pollution and all the different negative aspects of current power. And so 24/7, 365. It's a reinvention of electricity. As you know, telecommunications have been reinvented, pharmaceutical, biologics. There's constant developments in other fields where there's a resurgence or reinvention or redefinition of all kinds of structures in our society, even the way we communicate, the way we socialize now with social media and the like. And we're reinventing electricity. And I was watching, this is kind of a little bit diversion, but I was watching an economist, and he was talking about why the economy wasn't really booming like it used to. And in the early part of the Industrial Revolution, the big things were the internal combustion engine and things like electricity and aviation that so transformed society that it led to enormous growth and prosperity, creation of the middle class. And now with the event of, as much as we rely on it, with the smartphone and things like that, it really it's not as transformational as these fundamental inventions were. And this strikes to the heart of pretty much everything, because when we get to down to the sun cell is electrification. It is energy. It will affect aviation. It will affect even communication, because we can envision these autonomous cells forming a mesh network that could even be superior to the internet. So there's a lot of opportunities, just fundamental unprecedented opportunity in regarding this invention. So it's as I was saying, a new sustainable, non-polluting source of energy. Has been validated by many independent parties, and I'll go through the timeline. We've constantly had this validated. This has been validated from the very, very inception, and it just got better and better and better until there's a breakthrough moment that puts us in position now that it can be competitive with any form of power. Pretty much in any application of any merit. It's based on proprietary methods and systems, so as far as I'm aware, there isn't even anyone filing patents in this area. So we have a very, very competitive advantage in that regard. We're looking to do electricity sales based on a different kind of model than currently. We would have no metering. As you know, everyone has these, they're dependent on wires and central gen transmission. And this invention would free the world from central, the spider web going out from a big central gen polluting power station, and you'd have autonomous power with no metering. And we would lease it on a per diem basis with enormous cost savings to the users. And we're going to outsource the manufacture, the installation, the repairs. So this could ramp up very, very quickly. So you have small autonomous units that could go into mass production and take advantage of all the infrastructure that's out there to support, that already exists, to support the rapid proliferation, utilization of this invention. And we're transitioning from all the hard work, as I'll go through the timeline, on all the foundation that's finally culminated in a direct pathway to commercial launch of this technology through 2017 and 2018. And needless to say, it has tremendous, profound implications in terms of accessible, affordable, clean power, not only here in the first world, but for all citizens of the planet. So on the left is a schematic cross-section of the cell you can see there. That's an actual life size, it's a real unit. And it creates electrical power by using photovoltaic cells, which everybody's familiar with. These are a little bit more unique in that they run at extremely high light intensity. In fact, they run 2,000 times the light intensity of conventional photovoltaic cells. And they are a commercial product, and they're the field of application for that product initially that we're borrowing from is called a concentrator photovoltaic. There they use enormous parabolic dishes, something like 30 meters or 30 feet across, or 10 meters, and they concentrate the light down into the size of about a wallet, and get 1,000 times sun concentration in terms of its intensity, illuminating the photovoltaic cells. And that intense light, they're actually much more efficient, and they're designed to have multiple layers. So I'll get more in detail, and they actually do about 3 times the conversion efficiency of typical photovoltaics that you see out in these solar farms. So they're called triple junction concentrator photovoltaic. And the voltage output and the characteristics of our power source would be identical to that by design of photovoltaic, because we're using photovoltaic conversion. The footprint is very, very small. It can be something on the order of 75,000 times smaller than a comparable solar farm. They call it a solar farm because it takes a whole farm. Ours will have a very small footprint of about half a meter at very large power generation scales. The intensity of the light, as I was saying, is very high. Here we're going to run initially 2,000 suns experimentally now. Well, I wouldn't say experiment. In designs that are being tested in labs today, they've gone up to as high as 10,000 suns. And so 1,000 suns is 1,000,000 watts per square meter, just to give you an idea. And 10,000 suns will be 10 million watts per square meter. That's about the power of a central, or a, excuse me, you have a central gen, and then you would have substations. That would be the size of a very, very large substation. That's huge power. Like, there's only a few 10 megawatt units, and it takes a long time to get them permitted. That's very large power. That's about as big as power as you'd have on an enormous cargo ship, to give you an idea, or a super tanker. So that's a lot of power in a very, very small area, and it's very, very thin. It's like having a substation on a piece of cardboard or a chessboard. It's just out of control power density. So and what I'll show you is an example of how powerful this can be. It's more powerful than any known primary energy source. So if anybody says, well, I don't know if this really works, or maybe there's some other explanation, you can't create power of this magnitude and this intensity by any known power source. Like, if you take, you'll see things not only melting but vaporizing. The highest the highest temperature melting refractory materials. It's not only melting them, it's vaporizing them in seconds. It'd be like you turn on your stove and it would not only melt the grill but vaporize it, and that's an order of magnitude easier to vaporize than the materials we're using, very conservatively. So some more specs. It's a continuous power source, and it's very, very safe and non-polluting. It needs a molten metal matrix that creates a condition where you have extraordinarily high conductivity for the reaction, and I'll explain why So we use, and something that's very, very inert, so there's no other side reaction, so it will only support the reaction of atomic hydrogen to form a more stable form of hydrogen we call hydrino, which turns out to be the identity of the dark matter of the universe. And dark matter is something that makes up pretty much all the mass of the universe. You can see it by gravitational effects, but doesn't absorb or emit light. And the product of the cell, the sun cell, is in fact that, a new form of hydrogen that doesn't absorb or emit light, but you can see it in terms of it forming that state by a unique light signature, and then you can identify it by a number of analytical techniques that I'll go through. But it's extremely stable. As I said, it doesn't even absorb or emit light. And the chemical reaction mixture has vaporized silver, which is extremely safe, and it uses the hydrogen from water as the source or as the fuel. So hydrogen is being derived from water, which of course is about as safe as you can get for any kind of fuel. Compare that to gasoline or nuclear fuel, for example. So the cost is another issue. This is one thing that was very, very daunting to overcome, is to get enormous power density and get something that could compete with fire. I mean, fire is very, very tough act to follow. Internal combustion engine is a marvelous invention. It's basically, we're riding on the backs of the internal combustion engine. Otherwise, we'd probably still be in the fields hoeing beans or something right now. So, but it's very cheap. Like, it's per kilowatt internal combustion engine, and gasoline for what you get out of it in terms of work. I mean, take a weed whacker and you're out there, if you had to chop that by hand or saw a log by hand, you take a chainsaw and it just goes right to it. It's really phenomenal how much utility you get out of internal combustion engine gasoline. And it's phenomenally cheap. So this is actually even better. Our cost, capital cost, is comparable, and we have no fuel cost. The lifetime is extraordinarily long compared to internal combustion engine. There's no moving parts, and the power density is many. It's factors, very large factors of 10 that of the internal combustion engine. Extremely, extremely compact power source. So we're going to go the no metering and sell power very, very cheaply, probably a third of what you would pay on site. But our generation costs are much, much lower than this. It's basically the cost, capital cost of the equipment amortized over a 20-year lifetime with very, very low operation and maintenance costs, as I'll show. And it's scalable over very, very large decades of scale, from small units that you could use in the home to scales that you could put on super tankers, for example, or large trains, and ultimately planes. This could do basically any power application above the scale of, say, microelectronics and portable electronics devices and appliances. And it might even be scalable down to that small scale as well. So our plan is to deploy field test in 2017, and then do a commercial launch with initial units in 2018. So how much is energy worth? Just as a figure of merit, say you take a central power plant and you take power and it's pumped in this building through the transmission grid. So you have generation cost, you have transmission cost, you have distribution cost. All those have an enormous high capital cost in terms of infrastructure, and they have their own environmental impacts. And then you have demand charges. Let's say you want to put a bus charging station out here at the corner. You would have demand charges, because that would take a lot of cost and infrastructure to achieve that. So we have none of the above except for generation costs, and as I was saying, it's pretty much, and of course there's some operation maintenance. I'll go with that. So our capital cost could be as low as 10 to 1% that of conventional capital cost. 20-year lifetime is pretty much the PV, which is the predominant cost driver. Compare that to solar, it's extremely cheap. So per year, it's like $3 a kilowatt capital cost. If you cost the maintenance at equivalent to solar, which it is, you got about $1.20 a kilowatt annual maintenance cost, and then the cost of generation is like a $1 It's like, yeah, that's like 1% or less than current generation costs. So very, very inexpensive to generate. So, so one of the criticisms I've gotten is, well, it took you too long, so it can't work. And I would say we'd started out with a white piece of paper, and had to solve everything from subatomic particle masses to cosmological parameters, the analytical, the technological, the power source, and then get something that's competitive with fire. And unlike some inventions, this was as far from incremental as you could possibly imagine. There was nothing they incrementally built upon other than Maxwell's equations and Newton's laws. That's it. The only thing that could be utilized. And there's data out there of ionization energies of molecules and bond energies. There's massive amounts of the data. And suffice to say, over the years, the theory has knocked down one after another, and solved those problems over that 85 orders of magnitude of scale, and led to insight into how to create this energy source. So another thing that's very, very important, this isn't the scale by any means, it's not even that cute, but it does lay out the fundamental. It's 22 years of all this stuff that had to happen to get to this break point, so now we're within a product in 3 years. And it's not like a drug where you say, okay, I'm just going to do something called recombinatorial chemistry, where I just take a soup and I just shake all kinds of bottles of chemicals, take what comes out of it, and just screen them with robots. Because then if you get a failure, that's it. It doesn't really give you much insight. You just go get another bottle of chemicals and dump them in and do it again and again and again. But this is a little different because you have to, this involved solving the structure of the electron, then solving the atom, then solving the nature of the chemical bond, then solving the next thing and the next thing and the next thing, all the way up through cosmology, to prove that the theory was actually sound. And then to predict what experiments would identify that new state of hydrogen and how to get that reaction to work so it could, at a high rate, so that ultimately could be a new power source that would compete with fire. So, and we didn't have a lot of help. And initially, the initial concept was, well, we're going to, these are like quotes from Nobel laureates, and like, weren't too happy, albeit if you read now, the most common thing I read now is that the quantum physicists are saying that quantum mechanics has to be redone. It's fundamentally flawed. And I can, do you want to email me? I'll give you plenty of references. So, but in the beginning, they were very, very recalcitrant, and they were very defending quantum mechanics. Like, you don't have to defend the physical law because you can immediately prove it. But quantum takes it takes a lot of faith. It doesn't take a little bit of faith. And so we didn't get the world piling in. So originally the idea was, okay, we're going to make a heat source. We're going to prove we have a heat source. Everybody's going to be excited about it. They're going to help us build that heat source into a boiler. We're going to use conventional Rankine cycle, which is like a steam turbine, and we're going to replace fire, and everybody be happy. But then they say, well, how's the heat working? Well, it's making a new state of hydrogen. Oh, well, we defined the ground state of hydrogen in our math, and you can't violate that. I said, well, why not? Why can't the electron that's negatively charged get closer to the positive proton? Because we defined it that way in our math. It would violate our math. I said, well, I don't see why. There's no physical explanation in your math why. In fact, there's no physical explanation in your math for anything why it can't get closer to the proton. And physical laws actually explain why it's stable and gives a pathway whereby it can form that state. So we got into a lot of acrimonious exchange, which didn't help us make a power source. So there's a fundamental basis for how this came about. I mean, it wasn't something I just said, oh, let me just go scam everybody and say there's some new power source and it's totally fantasy, or there's no physical basis. I actually was working on free electron lasers, and I said, okay, I don't really believe the electron's everywhere at once, has no physical form, is a singularity, and the universe is made of math, and we're manifestations of math. I think there's some problem very early on in theory that they should have solved what an electron was, solved what an atom, so you know identically what it is, and you can predict intuitively how it behaves. So I was taking a course, and I was looking at Strategic Defense Initiative Organization by Professor Herman House to do a grant. This is Star Wars under Reagan, and I was solving how free electron lasers, and I had an idea how I could get that to work. And he said, here's a paper, and he later published it in the American Journal of Physics. And it talked about, well, what it dealt with was why accelerating charges radiate. And that to me was profoundly important. And the reason why it's profoundly important is if you take physics, the first thing you read is the electron in the atom is going in an orbit. It's not changing its energy, so it's got to be in a periodic orbit. And it's got motion, so it's got to be periodic to be stable. And then if it's going in an orbit, then it should radiate light and fall into the nucleus. And that's what you read. It should keep radiating light until it falls into the nucleus, and the radiation should get higher and higher and higher energy as it gets closer and closer to the nucleus, because it's getting bound tighter and tighter. That's the whole premise. As the electron gets closer to the proton, it gives off more energy. But doesn't. So why doesn't it? Well, you'll read in the next paragraph, it's because the electron in the atom defies physical laws. That's what it says. Go check yourself. Defies physical laws, the electron. So I'm like, wait a minute. Here we have a free electron laser. It doesn't defy laws. And in plasma, it doesn't defy laws. Synchrotron radiation doesn't defy laws. But as soon as it's bound to a proton, it doesn't exist. It's a singularity. You have to collapse a wave function. It's pure math. It's not even an electron anymore. So you're like, how is that? What did the proton do to it? Because we ripped it off and put it through a free electron laser, and it behaves like we expect it to. So I took his approach, and I solved what the electron structure would be. In other words, it emits and absorbs light, so it must act as a current. And you can solve current for antennas. I mean, people use Maxwell equations. They design antennas. They design power transmission. So why do we do that? We take the equations of what light is from Maxwell. We'll match it to the electron as a source current for the absorption and emission of electromagnetic energy, which we know the solution. And when you match it, you get this. And that allows you to calculate everything from subatomic particle masses to predicting the acceleration of the cosmos. Analytical expression. Fundamental constants only. No weird math, no virtual particles, and no things that don't make any intuitive sense at all. This is absolutely intuitive, simple math on all scales. And that should be. Physics on the macro scale and atomic scale are identically the same. So you say, well, if they were different like quantum proposes, when do they change? And what physics applies in between macro and micro physics? And it turns out it's the same on all scales. So this is quantum on the left here. And this isn't a molecule. This is a single electron in a one electron atom. And you say, well, what is this? Well, this is a probability density function, whatever that means. And it's supposed to have something to do with the position of the electron. But the way it's construed is the electron is everywhere at once simultaneously, a single electron. But that every single point where you see that gray, that is an infinite number of electrons for one electron. And they say, well, we only see one electron, one energy. We don't see an infinite number of energies when we go and measure electron. Well, that's because there's parallel world lines and parallel universes for every electron of the infinity of electrons for every particle, every atom, every composition of matter in the universe. So you can see it proliferates out to infinities upon infinities and upon infinities, and it's totally nonsensical. On the right is an analytical exact solution of DNA. Every single electron is solved precisely. And then you can image molecules. On the top, because according to quantum, you can't see electrons, they don't exist. Well, they do exist, and you can image them in molecules, and they match the analytical solution. Here's the hydrogen electrons here. Here's the hydrogen electrons. These are carbon electrons of different bond strengths, or different types. And all the parameters work out here. The energies, the bond angles, the bond distance, it's all analytical. So there's a picture tells 1,000 words. This tells you that quantum's wrong, that you can actually make a physical solution to what molecules are. They really do exist, and they do have a physical form that's absolutely predictable. So this is a comparison of quantum, even as a tool to do calculations. And this is as accurate as it possibly can be measured. It's analytical closed form expression. This is quantum, and it's just shotgun, pure random results. And then of course, if you get one right on the line, they'll tout, oh, how wonderful quantum did. But they don't talk about all the ones that are like up here. So these are some other examples. Again, you can solve atomic problems using physical laws, and it's absolutely exact for structures of boundless extent and complexity. And then I was criticized, well, we've never had any publications. We have 100 peer-reviewed publications. And I think they're really good. I mean, we're the only ones publishing, except there's like a handful from other validators that went on and published independently from us, but we've pretty much had to build an entire field, but we definitely have very prestigious and very extensive publications. So, I mean, like any theory, what good is a theory if it has no utility? If quantum is just a curve fit to known data, but it's not predictive. That's why there's nothing going on in physics of noteworthiness. There's no great inventions. That's why we don't have anything like aviation and electricity, the phone being invented, because we're using the wrong physical model. In this case, there's a profoundly important prediction. And that is that you can take the hydrogen from water, which covers almost the entire planet, some places a mile deep, and release enormous amounts of energy per hydrogen compared to burning. So there's the invention of hydrino energy from the theory. And fundamentally, the blue guy is a hydrogen atom. The yellow is an energy acceptor. So this is a new type of chemistry where you have energy going from hydrogen atom. There's a radiationless energy transfer to the acceptor. The energy is big, so the electrons are ionized. That's the resonant process that occurs. And then there's a second step where the electron accelerates radially inward, getting closer to the proton and releasing what they call continuum radiation. It's all wavelengths. It's not a single line like the spectrum of hydrogen atom that everyone's used to. And that's why it may have defied detection until the theory was invented. Because it's a very unique light signature in a very high energy region where there's hardly anyone in the planet that's actually studying that region. Now there's a lot of clues, and you would think something this important you'd be able to find it in nature. And you can. If you look at flares and what they call active corona, like shown here, it can put out the entire power of the sun from those regions, just from that really rarefied gas. I'm talking about not even vacuum. It's like not even a typical vacuum we make here on the planet. I mean, a very, very, very low background or a very, very low vacuum is what the pressure of the corona is, yet it puts out enormous power. And the other thing is, it looks like it's 2 million degrees, yet it has other species in it that would contradict that, or be counter to that determination. And you'd say, well, what's the basis of it being measured at 2 million degrees when the surface is only 6,000? How can the surface heat the gas around it up to millions of degrees when it's in contact with cold space? It's not really being heated. What is happening is ion spectrum are observed, and the ions are presumed to be created by heat. They can also be created by high energy light, and they can be cold, and that is the case. we see exactly the same thing in our lab. We create high energy light that ionizes cold gas, so the ions would indicate that it's millions of degrees if it was thermally ionized, but it's not thermally ionized. It's ionized by the high energy light, and it's actually cold. What's formed as a product of that is a more stable form of hydrogen that doesn't emit or absorb light. And that is the same characteristic of dark matter of the universe, which makes up almost all the mass. This is a mapping. This is ordinary matter, like hydrogen, which makes up almost all the mass of the visible universe. And this is the dark matter, which maps the same way, but it just doesn't absorb or emit light. It's at much greater abundance, and you can only see it by its gravitational effects. Again, this is another map of dark matter in the universe. So it actually exists. It's not some term that has no experimental foundation. It's actually very, very profoundly important in the evolution of the cosmos. So what is unique about this divide detection? Well, you see how this is a continuous curve, and then there's really sharp lines. In this high energy region of the spectrum, you should only see high energy lines. Those are from ions, like ionized atoms. But we also get this very, very broad band of light in a very high energy region. It's about 100 times more energetic than typical light you'd see off that would be of chemical nature. It's called continuum light, and it has this distinct cutoff. That light is coming from all over the universe. And it's very, very powerful in terms of its intensity. And it comes from regions where dark matter is formed. Dark matter is exemplary here in this dark ring. And the way you can observe it is because there's huge gravity. There's galaxies here that are sort of oblate and stretched. That's because they're being gravitationally lensed from some other place in the universe. So there's something here that has massive gravitational field, but it's not absorbing or emitting light like this other form of matter here, which is hydrogen basically. And what the constituents, or the makeup of the galaxies you can see here, which again is predominantly hydrogen. So we make a transition of hydrogen to this dark matter form of hydrogen, and that's a new primary energy source. You can burn stuff like coal, trees, and gas and oil. Internal combustion and burns gas, for example. You can throw uranium and put it in so it's really packed in there, and the neutrons will start hitting each other, and you can get fission, and you can do nuclear, so that's another way you can make power. But this is new. This is hydrogen atom, the dark matter form of hydrogen, making massive more power than anything as a power density than anything observed prior. Huge amount of energy per hydrogen atom, and it's perfectly clean and safe. So we can identify this new form of hydrogen by a lot of analytical techniques, and that was another part of that timeline to solve rotation, vibration, NMR shifts, total binding energy, etc., that we could use known scientific analytical instruments and uniquely and characteristically and unequivocally assign this new form of hydrogen. For example, here's a rotational vibrational spectrum of the H2 molecule, that's hydrino, having 1/4 the internuclear distance as ordinary molecular hydrogen, having rotational and vibrational energies that are 4 squared or 16 times higher. It has an ionization energy that's 16 times higher. We see in X-ray photoelectron spectroscopy. So we have multiple ways of characterizing this new form of hydrogen, and it can't be confused with anything else because the energy is so high, there's nothing known, and it's an integer squared that of ordinary molecular hydrogen. Nothing known that has those high of energies. So then it's how do we take this new power source and make it into something useful? As I said, one of the ways was to look at it from making central power, central gens like a 10-acre plant, looking like $1 billion. You got steam turbines, you got transmission lines, you got years to pay it off. First you have to permit it. There's a lot of work goes into making central power, to say the least. So I was looking for other ways of making power not going through central gen. And one of them was a direct plasma to electric conversion. We look at plasma sources to make power. Plasma consumes a lot of power, and we weren't getting a huge amount of gain out of it. So I was trying to take whatever gain and convert it back into electricity, because if you try and convert to electricity, you have to get like 4x. If you use electricity to drive plasma, you have to get like 4x in terms of energy, because the inefficiencies of going from, say, plasma energy back to electricity. So it needs to say it's challenging, and we tried a lot of ways, and at each juncture, at each increment of innovation, we learned enough to go on to the next stage, and et cetera, the point where we got to what you see here today. So we tried a lot of plasma cells, microwave cells, glow discharge cells, radio frequency cells, many, many examples. And then this was very close. This is a solid fuels innovation where I devised a way of using chemistry to create the constituents that react to form hydrino. You need atomic hydrogen, you need an energy acceptor, and there's a very, very favorable mechanism to make that by a chemical reaction, and we got really decent power densities. The only problem is we had to regenerate the chemicals, and getting 100% regeneration rate or a yield turned out to be a challenge. Next thing was electrochemical, because even there, that would have been a central gen design. We would make heat, convert electricity using steam in a boiler design and conventional turbines and generator. So this was actually a very, very elegant invention. We had it validated by leading scientists. It's very simple. We measure how much electrical power it consumes and how much electrical power it puts out. So we would charge it to make some hydrogen, and then we'd discharge it, and we got 40 times the electricity out compared to in. Validated again by leading scientists, unequivocally making extra power and energy. The problem is we couldn't get the power density up high enough, because as we run at higher and higher power density, the reaction's so powerful that it would destroy the electrochemical components. So the next thing was, well, what's inhibiting the rate of reaction? What is it that doesn't make this go at very, very high rate? Because one of the intuitive things that any scientist would have is if you have a new chemical state of hydrogen that's lower energy, it should do that spontaneously, and it could potentially do that at a very, very high rate, because everything we know about excited electronic states, that's the electrons at a higher energy, it goes to a lower energy spontaneously, and it does it very fast in most cases. So why isn't it in this case? Well, the reason is, and this came in around the fall of 2013 into the winter of 2013, is solving this fundamental issue, is you have the hydrogen atom that will transfer energy to the acceptor, and this is so much energy, the only resonant or matching reaction that it would accept the exact amount of energy required for hydrogen to transfer in order to make this reaction occur, that is to form a hydrino state, the acceptor would have to become ionized, and the reaction would have to be an ionization reaction. If you have an ionization reaction, then you're going to build up electric charge. And that's limiting. It's like when you're sliding your feet across or walking across the rug in the winter, and you touch a filing cabinet and you shock your finger, you snap. I mean, you theoretically could keep charging up indefinitely, and then your arm would like fry up like got hit by lightning. The reason that doesn't happen is because as more and more electrons accumulate on your body, it becomes higher energy, become higher charge, and stops that reaction. Similarly, these electrons build up, and it stops that forward reaction. So the idea is to use a state of matter called an arc plasma state, whereby the reaction actually increases the higher the current that goes through the reaction. So we drive a current through it. Typically, the more current you drive, the higher energy. That's Ohm's law, V equals IR. Joules per coulomb is higher, the higher the current. This is the opposite. The energy per charge actually drops the higher the current, and it recombines these electrons and ions, and the reaction rate becomes explosive, like that. That is 5 million watts of light, and it's essentially what you saw is a very, very small fraction. I'll go back and play it again. So that's a very, very small fraction of power. Almost all the power is in a region of the spectrum your eye can't see. In fact, the signature is very unique. There's essentially no visible light your eye can see, or infrared, heat light. It's essentially all high energy, extreme ultraviolet light. I've talked to a lot of people about this. No one's ever seen anything that makes a spectrum like that. Typically, you have a lot of infrared and visible and very, very small amount of high energy light. This is the opposite of that. And this is what the spectrum looks like with extreme ultraviolet spectrometer. Your eye can start to see about 400 nanometers and longer. And this is all in this high energy region. And this is what they'd call as close to infallible as you possibly can get in science. It uses a National Institute of Standards and Technology calibrated light source to measure the response of the spectrometer, and then it measures the power from our sun cell reaction, and it measures how much power it is relative to that calibration, and it comes out and gives us 5 million watts peak and over 1 million watts average power over that event. So it's a lot of power, and that's coming from something that's a couple millimeters in diameter. It's enormous power density in terms of power per volume. So the idea is, if we have this really powerful reaction, and that was high speed video, that is it slowed the reaction down so you could see it. That occurs over 1,000th of a second. So now it gets into innovation. So if you have something that makes 5 million watts of peak power and it's 1,000th of a second duration, if you could make that a reaction occur 1,000 times a second, then you've got a continuous megawatt power source. So that's the stage where innovation comes in. To make it at 1,000 times ignition per second. So there's a lot of different systems that were tested, and each one was incrementally better than the next. So one thing, if you want to know the details of it and actually see some of these things run, because they're really interesting, you can go to our webpage under demonstrations, under our webpage at Brilliant Light Power. And there's a video of some of these from the January 28th demonstration that we did this year, and it goes through some of these earlier generation technologies where we used powder matrix, we used slurry matrix and slurry pump, we used pellets. So we can make 1,000 of these little fuel pellets per second, and then we can pneumatically inject them, like shown here. We had a device that could fire those, so we could sustain this reaction at a high rate, so we could get an averaged high power output. This is one of the most, let me just explain this one second. So, next video I'm going to show you is a demonstration we did July 20th up at our engineering firm, Columbia Tech. They're in Westboro, Massachusetts. They have about 400 engineers. They do all kinds of very, very sophisticated engineering for a lot of big household name companies over a really broad space of everything from material science processing to gene technology to medical instrumentation. And we ran a demonstration up there, and you'll see this has a progenitor of the sun cell. We're injecting molten silver with electromagnetic pump. I'll explain that a little more. And we're using tungsten, very heavy tungsten parallel plate electrodes, and they vaporize in seconds. This is a very, very powerful reaction. So you're going to see the video of that now. So this is a glove box. This is a controlled atmosphere inside this chamber. It's human size, so this is really big. This is not a small little laboratory device. That whine is the overpressure alarm on the glove box. because there's so much thermal power and energy released there, it overpressurized the chamber, and you heard the clicking. It was trying to equalize the pressure before it blew out the glove box, and the alarm was going off. So that is a lot of power. That's a big, big device where that little tiny cell was initiated. So afterwards, here's the cell, and there's electrodes that's supposed to be here. Tungsten, big tungsten bars, and they were not only melted but vaporized, because we could detect tungsten ions in the gas phase. That's like 6,000 degrees centigrade. I mean, that is super, super hot. So, so that required some more innovation. What it proved is that it can make more power than anything known, and it also proved that it would vaporize the cell and vaporize electrodes and destroy itself in a matter of seconds. So there's some nice, clever innovation that went into engineering around that, and namely, what you can see here is the device now is made out of carbon. And carbon can go up to extremely high temperatures. It's called a refractory material. It has, tungsten has a melting point of around 3,700 degrees Kelvin, and this actually will start to sublime at 4,000, and that's plenty hot enough. We want to go to 3,000 Kelvin and then illuminate a photovoltaic panel. So basically we're making an enormous light bulb. So when you think of a light bulb, like an incandescent light bulb, you have a filament, like a little wire in there, and it's a very small area, and you put a ton of electricity through it, and it'll glow white. You know, you turn it on, it's on instantly, you turn it off, it shuts off instantly, and it's creating that light because it's hot. So it's so hot, it's not emitting heat, it's emitting photons that your eye can see. It's in a regime where essentially all the power is being lost by emitting light. So it's instant on, instant off, more or less. So this is the same idea, but rather than a little wire, it's that entire surface. So you're getting tens of, not 100,000 times more power coming from that surface rather than a little thin wire. And it's the same light that you would see from an incandescent light bulb, and then we would convert that into electricity using the photovoltaic cells. And at that temperature, 3,000 Kelvin, the intensity is around as high as 5,000 times that of sunlight on the Earth's surface. So it's very intense, and it's point blank right into the photovoltaic cells, and it's 365, 24/7. So it's not like the sun coming up and down and things like that, and it's super, super, super more intense. So therefore you can use concentrator photovoltaic and use like 1,000 times less photovoltaic panel area and shrink it, and therefore you cut the cost dramatically. So this also, in addition to refractory material, it has molten metal injectors. So there are no electrodes. It's molten metal. And you're like, well, how can you destroy molten metal? It's already destroyed. So it's kind of like a constant regenerating electric ignition system. And you might look at that, and then you know, actually, this is it. This is the device right here you're looking at. Is identically that. And you might look at that and say, well, I don't know if this thing's going to work or not. But I'm going to show you at the end. It works great. I mean, it actually works beautifully. And this is the device. And it's and looking at the engineering, and we have a full tilt into the engineering program now to build the field testable unit in the first half of 2017, do field trials, and engineering is going full tilt. It's basically right now down to the sensor systems and the controls. And for example, there's 2 reservoirs here that have molten silver in it. We have to control the levels of that and sense that. And we have to control the whole thermal management from the input of the thermal sensors. So we got some very elegant technology, and we're building and testing that. And once that's implemented on the cell, then it's ready to go for integration of photovoltaic and then out to field trial. And the photovoltaic converter is being separately built. And again, it's a bolt-on part, which I'll show you more detail here, that's being built by Musimo, which used to be Spire. They used to be the ones that had, they were one of the top, they had at one point the record for the most efficient concentrator photovoltaic. They're like 40% conversion efficiency. So they're very proficient at what they're doing, very knowledgeable in the concentrator photovoltaic space. So as you can see, there was not idle hands and there weren't failures during those intervening years. And all that technology was absolutely necessary. The theory, the hydrino predictions on terms of signatures, the analytical work, the power cell development, the kinetics, the validations, the publications with feedback from reviewers and other external parties, and then ultimately getting into engineering and commercial power design, and even the business model, which Dominic Jones is going to talk about later, to get a model that works with the current infrastructure and price structure and competitive economics of the existing power industry. All that had to be developed from scratch. And it took all these intervening years to get to this break point where the kinetics was solved, and then from that point it's a new company, and it's 3 years thereabouts from inception to a product. So the way it works, again, I alluded to this, is you have a very, very bright light bulb inside of a photovoltaic dome. So it has two pumps, and you can see two reservoirs here. There's on the bottom there, you can see some magnets, there's magnet holders, but there's some apparatus underneath. And what that is there's permanent magnets that are transversed to this loop, and then there's current that goes on this vertical axis, and the combination of the permanent magnetic field and the current causes a force in a molten metal that pushes it through that tube and creates pressure and pumps it, and then it comes out these nozzles, and the two streams hit each other, and when they hit, there's electrical connection on each one of opposite polarity. When they hit, the current flows through that molten metal, and you have a source of hydrogen and a source of catalyst in that stream, and you get the reaction. Then there's other support that goes around that reaction. So you have the black body radiator, so this reaction is occurring inside of this graphite sphere you see. It gets super hot, emits white light, and then this gray structure out around it is a geodesic dome comprised of photovoltaic elements. So they have little tiny concentrator photovoltaic cells tiled on triangular elements, and the triangular elements connect together to form a geodesic dome that's expandable and scalable to form the photovoltaic converter. There's an inductively coupled heater to melt the silver to initiate it, so that's just during startup. And then there's heat rejection. There's a water pump for circulating for cooling. There's a vacuum pump to control the gases initially to get it started. There's a outer pressure dome that is filled with inert gas and a source of hydrogen, so that the hydrogen permeates through this black body radiator and resupplies hydrogen. And then there's a constant catalyst inventory, a constant silver inventory inside, and all you're doing is supplying the hydrogen. This outer dome equalizes the pressure on the inner reaction chamber inside there. So there's no net pressure across it. So it's super safe. The pressure on the outer dome is about that in a bicycle tire. So that's what that outer dome's purpose is. So this device creates intense, very intense, predominantly short wavelength light of this nature, and we convert it by having it absorbed by this carbon sphere, this guy, and then he'll re-emit it as this type of radiation here, which is in the region that your eye can see. It's visible and near infrared, and this is the chopped up spectrum that different layers of the photovoltaic cell convert into electricity. So this layer would convert this wavelength region, that layer would convert that rate, so it would get the middle region, and then the longer wavelengths would be this red, this layer indicated by the red trace. So that breaks this light up and very efficiently converts it into electricity. One thing nice about the PV, in our case, let me go back here, is any light that's not converted by this PV dome can be reflected back to the black body radiator and reabsorbed and then re-emitted as the higher energy black body light. So we can do light recycling. You can't do that with a solar farm. If it reflects off the solar panel, it goes back out to space. So we conceivably could get much higher conversion efficiency by doing light recycling. So if you compare it, that's one advantage. The other advantage is if you look at a solar farm, it is enormous. And you can say, well, I don't want to panel the entire landscape with these photovoltaic cells, so because that's expensive. I mean, you have to make a lot of photovoltaic cells. So the Chinese came in and they just said, by brute force, we're just going to panel everything. An alternative was to use the photovoltaic cells in a very small region, because this was expensive stuff, and then use parabolic mirrors to concentrate the light. It's some advantage because you cut back from all this being PV to just this being PV, and this could just be mirrors. But the footprint's still the same. They're both 250 acres. 250 acres for 100 megawatt in both cases, because you're not concentrating the sun, you're just collecting what's there. So you haven't changed the intensity of the sun on the Earth's surface, so you still have the same footprint, but you've cut down the amount of PV material. Contrast that to the sun cell. The sun cell creates light of thousands of times more intensity than sunlight, so you can cut down the scale, and then you don't have, you can increase this power density to very, very high intensity, and then the footprint becomes as much as 75,000 times smaller than a solar plant like shown here. So you replace this with a device of that scale. I show here on the table. So there's some other parts, I'll just kind of run through them. We have cooling plates on the outside to cool the pressure vessel. And so this is the PV panel. There's some, this takes, I'll get through some of the parts. So we're using all known parts, all known technology. Like the electromagnetic pump, 60 years maintenance free. It's used in the nuclear industry, it's used in chemical industries, and we're using the PV material is concentrator PV, so it's like triple junction, using things like gallium arsenide, indium gallium arsenide, aluminum indium gallium arsenide, known materials using metal organic, continuous vapor deposition type technology. The reactors, all known. There's the same reactors used for existing PV and for LEDs, light emitting diodes. We're using inductively coupled heater to heat it up. That's used in the metallurgy industry. We're using refractory materials, again, from high temperature metallurgy applications. We're using supercapacitors for the ignition system. That's from energy storage technology. Again, so known technologies applied to an entirely new design and primary power source. But we're not reinventing the parts. We're using parts that are known in industry. So then this is showing the inductively coupled heater. This is sensors right here for the silver level and those reservoirs. That's one of the primary focuses of the current work. And then you can see this inductively coupled heater. It has an actuator arm that moves it up and down, so it can control the power and control the position, so we can warm the cell up and get it in the startup mode, and then drop it and use it for a cooling system after we initiate the reaction. And then there's some gases that control the atmosphere in the outer pressure dome, and we can supply hydrogen by tank hydrogen, or we can create this by electrolysis of water. So we can just use water. If we use water directly as the source of hydrogen, you're looking at less than 1% of a parasitic load for creating the fuel from water. Showing more of the parts, there's a power source to run the inductively coupled heater for startup. There's the ignition power source. This is the power source to run the electromagnetic pump to inject the molten silver, and then there's a battery to start it up. There's a water tank you can use for the fuel tank and for cooling. Then there's a radiator cooling system to take circulated water that goes through the electromagnetic pump, cools those components, and the photovoltaic predominantly. So here's some more pictures. We got a graphical interface to control the system. We're planning on starting it up and running it at constant full power. So this will be running like 150 kilowatt constant power. If you want to do power switching and change the power level, you would just dump the remaining power into resistor and it would be rejected in the radiator. So it'd be like the heat rejected in a car, but you would have constant maximum power essentially instantaneously for all practical purposes. So again, some more schematics of that. Then there's an external power connector here. And these pictures are on a web page. So this is what it looks like packaged up. So it's got the outer dome, it'll have a housing. And it's made so you can pull this off and quick change out parts and repair it and get to access any component in it, modular and interchangeable very quickly. So this is a schematic of the parts. Again, I was saying all these are existing in terms of known technology or parts, like the supercapacitors, the EM pump. That technology is known. Some of the cooling systems, the materials we're using. Again, it's not that demanding in terms of the number of parts or the complexity of the parts. Again, there's no moving parts in the system, so the main component in terms of cost is almost entirely the photovoltaic, as I'll show you. So this is the bill of materials of those parts for a 250,000 watt unit, first of kind. This is not mass produced. So that would come out to be roughly $25,000 for a 250 kW, about $100 a kilowatt. That's super cheap. That's like less than 10% capital cost of other competing technologies. You have no fuel cost, and it's on-site power 24/7, 365. So the real driver is, you can see here, once you get up to any kind of scale, it's essentially all the photovoltaic assembly. And as that gets more and more mass produced, the National Renewable Energy Lab's even predicting that could get down as low as $30 a kilowatt. So the capital costs of the primary part could become very, very cheap. And that would have an estimated 20-year lifetime and have an operating maintenance cost of about 2% of the capital cost per year, which is really, really insignificant. And no fuel costs, no pollution. So the current program is to make a continuous engineered prototype, completely computer controlled, so we just press it and it all does startup, it does the injection, it does the ignition, and runs pretty much, and cooling technology, all running on terms of autonomous operation. And then we put the chemistry in it, and what I'll show you in a video of this actually operating, once the ignition, it creates enough power that the silver vapor pressure gets high enough, you can turn the ignition off, because the silver vapor is conductive enough to cause the recombination function to occur without the injection and without the arc current going through the plasma. So it supplants that crucial function. And I'll show you, we actually turn the ignition power off in this video, and it sustains for a while, and it cools off, and then by the second time we turn it off, it sustains indefinitely. So you can actually turn the power off. So this would be something that we would start up with the ignition system, comprising the arc current. We would heat it up and become a molten state. That would be the inductively coupled heater. We turn that off, and then once it gets into the 3,000 degree operating range, the silver vapor pressure will be very substantial. It's basically boiling. It becomes a boiling silver boiler, no net pressure across the dome because we're equalizing it with the outer pressure chamber, again about the pressure of a bicycle tire, and you can stop the injection at that point. So this would ultimately go into a self-sustaining mode without any input power. And I'll show that in a video where we turn off the ignition system. So, this would be the goal of this of the next prototype where we run the chemistry and then start turning off systems. The alpha prototype would integrate the photovoltaic, and then that has a single junction. Then we're going to go to a double junction with twice the photovoltaic efficiency, and then the pilot would be a triple junction with light recycling and running at a higher operating temperature, so we achieve at least 100 kilowatts electric, and that would be going into our initial commercial applications in terms of initial deployment. So this dome, to give you an idea of the power level, is a 6-inch diameter dome, and running at 3,000 Kelvin, it would emit about 5 million watts per square meter, and that would translate into about 330,000 watts of light. So if you had 10% efficiency, you would have 33 kW. If you had 20%, it would be 66 kW. If you increase the temperature, and then if you got if you got triple junction PV up to the range they're at now, you'd be at 40% conversion efficiency. So you'd be around 120,000 watts with that electric. And then if you increase the temperature from 3,000 to 3,500, the emission goes from 5 million watts per square meter to 10 million watts per square meter, and you would double the power. So at that point you'd be up to somewhere around 300,000 watts of electricity. So it's really how much light does it put out and how much conversion efficiency is a PV capable of. So that's what the different versions of the cell are, because the black body temperature and its scale is fixed, and then we can increase the temperature and go from 5 million watts per square meter to 10 million watts per square meter, and then it's just how efficient the light conversion is between 330,000 watts of light and 660,000 watts of light. How much of that light is converted into electricity determines which generation prototype we're on. So this is a video of the cell operating. So what we have here is there's a gradient here for the molten silver to flow back. So we have the electromagnetic pumps pumping the molten silver, and we have the pressure low, so they're hitting the hill and rolling back. And then we're eventually going to turn up the electromagnetic pump pressure so the two streams hit. Then we're going to start the ignition, and then as we go through the video and we get the plasma, it'll get hotter and hotter, and we'll shut off the ignition system. We'll turn it back on again. And then the second time we shut it off, it's in self-sustaining mode. The ignition system does not come back on, and it basically is in a mode where the power runs without the ignition system. So what I would like to do while that's running is take some questions. Yes?
So if this technology is going to replace basically all other sources of energy, right?
Yes.
And you guys have the intellectual property on it.
Right.
So you're telling me that you're going to be like the first $1 trillion company, basically. I mean, that's how huge it is. It's like trillions and trillions of dollars of that.
Yeah, the electricity market is 3.5 trillion a year. And I think the U.S. market's like 387 billion, something like that. Then when there's cars, cars actually don't utilize the power as much as stationary, obviously, but it's huge. I mean, the cars, like 4 months car production is like the entire U.S. grid.
Yeah.
Because if you look at the capacity of that inventory of generation assets, and there's like 68 million cars made a year. Now you see we started the ignition here. You'll see a section where we turn the ignition off, and then you'll turn it on, and then we'll turn it off again because it's hot enough, and it'll just sustain that plasma without the ignition. So, yeah, so it could be a very valuable company. We're looking to do revenues from per diem leasing of the of capital equipment, where we own the equipment, and then we have installers, and Dominic will go more into it. But there's companies that do utility work, and they might do like $1 billion a year in sales. There's some fairly large service contractors for utility industry and others in the power equipment space in terms of services. And we have a number of those big companies that have agreed to do the installations. So in the case that we don't do a grid connection, there's no utility regulation. So we're looking at a underwriter's labs approval and a local permit for a generator. So our model is to be not connected to the grid, and until there's some reliability numbers on the technology, we could give redundant power, because remember we're like a millibuck per kilowatt hour, and which is like as low as 1%. So it's actually cheaper for us to put redundant cells to then even have urban grid, which is like 1 to 2 cents, like transmitting even between these buildings. Be cheaper to have redundant capital equipment. So, and then we're going to outsource, in addition to the, we'll do the manufacturing, supply chain management, installation repairs, depot repairs, and then we'll just be doing per diem leasing with no metering. And even with phenomenal savings to customers, the recurring revenue for even very, very small deals becomes off the charts, as Dominic's going to show you some examples.
Okay.
You got any more? Yes. Additional question? Do you have additional
question? If I make a statement, this is so incredibly potentially disruptive to the entire world. I'm shocked that I don't see representatives from, for example, the State Department here. I mean,
yeah, that is kind of curious, isn't it? And I think it's because the quantum guys say it's impossible, and we define the ground state, and everybody believes in quantum, and it's a lot of the perception is just distorted, because we have working devices. We have 5 validators. You can go on our webpage that have validated the power at million-watt levels. I mean, there should be, this is like even ignition is putting in the power of like a hair dryer and vaporizing tungsten in seconds. I mean, anybody with eyes can tell that this thing's making an enormous amount of power. We have 15 different analytical tests to show this new hydrogen. Even astrophysicists are saying the dark matter of the universe is some unusual form of hydrogen, and we're actually matching the spectrum they're seeing coming from all over space. It is glaring problems it solves, like why does the gas around the sun look 2 million degrees when there's like carbon monoxide molecules in that gas? I mean, there's so many obvious things. Like, what is the identity of dark matter? The universe is made out of hydrogen. That's basically it. It's hydrogen. But that's only a small fraction based on gravity. So what's the other stuff we can't see? It's hydrogen too. I mean, there's just so many obvious signs out there, and I just think it's really just incumbent politics in the academic in the theory circles. They're really pushing policymakers away from this, and I think they're really missing the opportunity.
See what happens.
What's that?
Plan just to put it out there and let the chips
That's
fall?
exactly that's exactly our strategy. Yes.
Is that the size of the commercial unit?
That's the actual unit itself. That's the unit it's running right now.
So does that one actually run? Or is
It's running right here. That's it. It's exactly the same as that.
How many hours do you have on that?
Well, there's a couple components in it. The electromagnetic pumps. See, now you put the ignition back on, and then it was off. Then they'll turn it off again. It's on now. The components in the bottom, the electromagnetic pump, 60 years maintenance free. We could run that indefinitely.
But the actual system, how long?
Well, right now this is open.
Okay.
This is open, so the silver vapor will be lost in time. We have to close it, but then to close it, we can't control the pumps by visualization, so we have to have all the automated systems.
Okay, so when you're going field test this, how many hours are you intending to put on?
We think this unit will be limited by the lifetime of the photovoltaic. Again, the pumps, there's no moving parts. The only thing that's really a key component in terms of moving material is the electromagnetic pump. They're known to operate 60 years maintenance free. It's a known technology.
No, I get
Then you're
that.
heating
Your
up.
system, how long have you run?
We can run it in this case. In this case, it's running, and it's running the duration you're seeing it now, and then the vessel which it's in overheats and systems start deteriorating and failing because of the high temperature. We have to build the.
Right, so it is just theory still.
No, it's not theory. It's measured,
No, it's
validated by five validators to be 1,000,000 watts in a coffee
I
cup.
get it, but it's not. It just hasn't been done.
That's correct. It's in the process of being instrumented so we can run it indefinitely. But it's running right now, as you can see. Yeah. Now it's a matter of it gets too hot, it starts melting stuff, it starts blowing water coolant lines, and we can't maintain the levels manually other than having it open, and then we lose silver vapor because it's vaporized. So we need to close it up with the instrumentation, and then it should run indefinitely. So it's engineering, and we've had the engineering firm has said all engineering issues are solved. So it's basically implementing the engineering designs we have now, making it into a field testable unit. It's not theory, it's working. Yeah. Yes.
So, what do you think is going to happen to the field of physics? I mean, because essentially the implication here is that physics has been wrong for like a century, right?
Yes. And there's actually an article in Nature, and I couldn't believe it, that they actually said, and I can give you a reference. You want to email me that they believe that theoretical quantum physicists have been engaging for fraud for a century. I mean, they're basically saying the universe is math.
Yeah.
It's not. It's hard stuff.
I mean, this is going to upend the entire field.
Well, no. Most of the world uses classical physical laws,
Right.
and there's a very, very small, very vocal, very powerful subset of physicists called quantum physicists, which are really mathematicians. They're not really physicists. Like if you ask them how to solve any of these problems in terms of physical principles, they wouldn't know how to do it. They'd start out with some basis sets, and they'd start out with, SU1 and this and that, and all kinds of math, and talking about extra dimensions and symmetries and whatever in the math. But they don't really understand. Oh, you have charge and mass, and you have fields and forces, and you solve physical problems. It's a different approach. They say, let's just take some big math, and this piece of math corresponds to this, and this piece of math corresponds to an electron. And no, electron's really something that has charge and mass, and you can create it from a photon, and you can describe it in terms of physical principles, not just pure mathematical principles. So I think what it'll do is physics will revert back to physical laws, and math will be for computer games and other applications.
Okay.
Yes.
Can I ask another question?
Yeah, go ahead.
I'm sorry. So basically this reaction produces these hydrometers, and their hydrometers, as I understand, are so small they'll basically just leave the unit because they can escape through the spaces of the...
Yeah, it's 64 times smaller in volume than the hydrogen molecule, and hydrogen molecules permeate through very readily.
Okay, so you're also producing oxygen from this, right?
Now we have a constant oxygen inventory inside, and the silver inventory is constant as well. We have an oxide in there that provides the atom we need to make an HOH nascent HOH molecule to accept the energy from the hydrogen atom to form the hydrino form. And the reason why we use that nascent HOH is because that energy of the molecular orbitals in that molecule, which is a water molecule but not interacting with any other species. It's like an iron atom versus metallic iron. So as an independent species, the molecular orbital potential energy is an integer of a Hartree, which is the potential energy of uncatalyzed hydrogen. That's the characteristic you need to accept the energy from hydrogen to have it go to this lower state. Yeah, in the end there it was in the self-sustaining mode. And then at this point, it's so hot, it's starting to pop water lines, and so that's our goal right now, is to get all the sensors and close the system up, and then it should run indefinitely. We'll put the PV on as a separate component. But and yeah, let me answer a few more questions. Yes.
So, Randy, I'm trying to understand the relationship between your production of heat and light.
Yes.
And if I heard you right earlier, you think the concentrated solar will be about 3 times efficiency of conventional PV, so I'm thinking 50 to 60s, 50s maybe in there.
Probably conservatively 35, 40.
Okay.
With lights recycling and triple junction.
Okay, so but you're also producing heat, and combined cycle unit will give you better efficiency than that. Why the decision to use photovoltaics as your pathway to electricity as opposed to boiling water or doing something else?
Well, it has to do with the power density. Like if you take a heat exchanger, like if you take a heater, like heat exchanging and heat absorption are kind of a little bit reciprocity in terms of their function. So a heater, you can only get maybe 10 watts per square centimeter. So in this case, you're getting more than 100 watts per square centimeter.
With the size function.
So yeah, it's size. So you'd have the heat exchanger would be a very big box. It's standoff to get the area to be able to accommodate the acceptance of that amount of power, and then you'd have to have a pressurized system. You have a steam system. You have to have an operator. You have to do it in terms of scale. I mean, the turbines typically run up to 10 megawatt, 100 megawatt scale. And then you have to have a cooling tower, because if you recirculate the steam and have a closed system, the efficiency goes to very, very low. It's probably under 10%. So you say, well, I've got a steam cycle, I'll go 30%. But that's because you're using the river as your heat to dump the heat into. But if you take that heat and you try to dump it into air and recirculate that water, it's going to, all your efficiency is going to crater really quickly. And the other thing is, the answer to your question about the heat. So all the power that comes out is in the form of black body radiation of 3000. So what that looks like is, so it's got a characteristic spectrum. Oh, a second. So it's got, this is what the black body curve looks like at 3000. So it's got heat in it too, but it's got visible wavelengths, and then you get a PV that'll take most of that spectrum and convert it to electricity at some level of efficiency, and then beyond a cutoff like 1800 microns, it won't, or 1800 nanometers, 1.8 microns, it won't convert it. But that light can bounce back. If you gold plate the back of the PV, gold's almost 100% reflector of infrared. So all it comes out is coming back to the black body radiator, which has a emissivity of 1. That means it absorbs everything that hits it. And then it maintains that black body temperature at 3000. It comes back again at this higher energy light spectrum.
So your actual efficiency is higher.
If you do light recycling, it can be pretty good. So then what doesn't get converted, let's say you have light recycling and you get 30, 40%, then you're getting 60 to 70% you're rejecting. But the PV has, as shown here, this plate is what they call a microchannel plate, cold plate. So it has copper to semiconductor bonding, and the copper transmits the heat into microchannels. They're electrodischarge machined into this microchannel plate, and they're extraordinarily efficient at removing heat, much more than typical heat exchanger. So the whole key, the concentrator photovoltaic, is not the PV per se. It's super cheap. What's expensive is and high tech is the heat rejection or heat removal from the PV. To keep it in an operate.
The heat aspect of the process is actually a nuisance then, because what you really want is the light.
You want the light, and any heat that, or any of that power that doesn't get converted into electricity of that 3000 black body emission, it goes into the microchannel plates and it's rejected. But it's rejected at fairly low temperature. Typically, the PV will operate at under 100 degrees C. So you probably run around 80 degrees C.
And I was wondering if there's a waste heat application.
It's low grade heat, because in this application you want to keep the PV cool, so you're going to run the PV under 100 degrees C, so you don't have a phase transition in the microchannel plate. You could, if you had a phase transition, it would cut the cooling down dramatically, but no one's really explored that area. Right now, what you're buying is concentrator PV, where they're running at about 80 degrees C, and then rejecting it in a cooling system, like a water-air heat exchanger that returns the coolant probably about 40 degrees lower temperature. So you're just dumping 80 to 40 into the atmosphere. Yes.
Randy, quick question. Once you have that continuous reaction, you achieve that certain spot. For safety reasons, I mean, would you, if you had a cutoff of some sort?
Yeah, you could
cut off the
purge out the hydrogen.
Yes, cut off the hydrogen.
Right. That's pretty much your safety feature. I mean, during startup, you can cut the pumping, you can cut the ignition, and you could let it cool down. But once it gets in that self-sustaining mode, you would cut the hydrogen.
Quick question.
Yes.
You have 100 peer reviews, 5 independent validators, but nothing from Princeton who's in your zip code.
We had some people that were interested in Princeton, but they got a lot of pressure from the physics department not to work with us.
That's kind of the road I was going.
Yeah, we did. We pursued it, but they're really vested in the hot fusion program, and they have the Institute for Advanced Studies, so they're really vested in string theory and some of these really exotic mathematical constructs of the physical, well, not the physical world. They don't believe in physical world, but they have they're pretty vested in theory that I don't think is the correct theory, and it just wasn't politically correct. Albeit we've had people that really love our work and would love to work with us. It's just peer pressure more than anything. But we invite working with Princeton for sure. It might be a little late. I mean, now we're moving towards commercial devices, but there's always room that we could collaborate on some project. Yes.
So, forgetting the device for a moment, can you explain the cosmology of this all? I mean, you start with a Big Bang, and substances are in what form, and how do you get to 90% being in? I mean, is the universe sort of running out of energy, or it started, or?
Well, there's a whole
happening in the sequence.
Well, as it regards
the universe deriving this energy. I mean, it presumably derived energy out of.
Yeah. Well, there's a whole. We can spend time on cosmology, but as it relates to our technology, we don't even have to talk about theory. We just have to talk about experimental data. All right. So you can take the gases around the sun, and they look like they're 2 million degrees because it's presumed they're creating these ions by thermal ionization. But there's other species in that same mix that would indicate that they can't possibly be that hot. So how do you create these ions? By some other explanation. Well, the way the sun works now is it might take 100 years from the fusion energy to permeate out through it to get to the surface. So obviously that's not causing these quick transient of flares and active corona. It's an enormous amount of power. It can't switch on and off and diffuse through and make these huge bursts of power. And so there's no real good explanation for that or why that gas looks so hot, other than there has to be some other power source. And what I'm saying is the spectrum that we create in our lab creates the same types of ions that they're seeing in the corona. That you can have hydrogen atoms go to this new chemical energy state and release not typical chemical energies, but something 100 times plus that kind of energy and create that signature. There's that. So that's just pure data. Then if you look at the white dwarf stars where there's no gas around the star that can get ionized, but you're looking right at the surface because of enormous immense gravity, you see those cut-off bands. In other words, there's for different transitions of hydrogen go to what we call the half state, the third state, the fourth state. The same as hydrogen go, the N is 2 state, 3 state, 4 state. It can go to half, a third, a fourth. In other words, rather than twice the radius or 3 times the radius of the hydrogen atom, when it gets excited, when it absorbs energy, it can go to half, a third, a fourth, when it transfers energy to an acceptor and drops down to this lower state. It's a different mechanism. You have the energy transfer, and then you have this continuum high energy light emission that would have a predicted cutoff of that continuum emission at 91.2 nanometers, 22.8 nanometers, 10.1 nanometers. That's seen. All those bands are seen when you can look directly on the surface. You can see those reactions, the reaction signatures.
What the sun is doing in these flares is creating hydrogens.
Yes, and in the corona, hydrinos.
Presently makes up 90-something% of the mass.
And you can see it occurring in white dwarf stars.
90% of the way to the end of existence.
No, that's a different question, because
I mean, how did these? I mean, I guess the sun got this energy by thought.
yeah. Well, don't confuse. Just forget about cosmology for a second. There's the universe has for example, just as an estimate, 10 to the 54 kilograms of mass. That mass can be converted into energy. It can go under fusion reactions, and it can go other types of energy.
Started as energy.
You could even annihilate. You could take the mass, 10 to 54 kilograms of mass, and maybe someday it'll all annihilate and all be light. The point of it is, the universe right now is pretty much matter filled. It's got enormous amount of potential to release energy. Some of the power release that's occurring in the universe now in stars and interstellar media is that power, the origin of that power is creating hydrinos, because it's making the characteristic light signature of hydrinos, and it is a autonomous power source separate from fusion that can explain very fast transient events, very localized events like in the corona, where the corona can be hotter than the surface of the sun by an order of magnitude.
Well, I mean, I do it because
or more.
I mean, so I'm climatology, not all of this stuff, but what's really important in the climate thing is to be able to explain a whole time history of things, not just sort of one flash of something. I mean, when you're going to come up with a new hypothesis about whatever it is, you have to be able to explain a full range of conditions, not just sort of pick and choose. So I'm just trying to understand how this all fits in with the history of the universe or something like that.
We could cover the history of the universe in another lecture, but all I'm saying is there's something out there experimentally that you can observe.
We switched presentations.
Okay, I just want to show him just graphically.
I mean, that solar picture was a sort of hole.
Yeah.
I think I know which one.
Yeah, so we can go all the way back to the flare and then the dark matter ring. All right, so let's just make it simple. Before we start doing the whole cosmos, we just start with a mystery. Like, you don't have to know what happens to the entire energy inventory of the universe to just say, how's the sun shine? Is it coming from fusion? Is it fusion plus some other chemical process that's the source of the power? What I'm saying, it's both. And you say, well, what's the evidence that it's both? The spectrum that emits, and the power emits, and the time duration that emits. There's another thing. You say, okay, what's the universe made of? You're just looking out your telescope, and you say, well, the universe is not only made of hydrogen and some helium and some other ions like some metals and things like that, but there's something else out there that has a huge amount of gravity that doesn't emit or absorb light. We can see it.
Well, you can see the effects of it.
You can see the effects of it. You can see it right here. This is it. This is the European Space Telescope took this picture of dark matter. That dark ring that's not emitting or absorbing light has a huge amount of gravity because this galaxy is not really there. If you turn the telescope, it'll disappear. You change the parallax a little bit, it'll move somewhere where it's not supposed to move because it's being gravitationally lensed. So you say, okay, there's a huge amount of, something there is creating gravity and it's not absorbing or emitting light. That's an observation. What is it? Well, you go through a deduction. You say, okay, everything I can see is hydrogen. All right, where is it distributed? Astrophysicists thought it was on the halos of galaxies because if it were intergalactic, it would have to be obviously hydrogen because it would be baryonic. The only thing with that much inventory is hydrogen. Now they found it to be the case. It actually is intergalactic. How they determine that? They look at debris from colliding galaxies and they form massive gravitating bodies that were comprised of dark matter. So it had to be intragalactic based on the distribution in the collisional product. The other evidence is if you actually look at collisions of galaxies like Abell 520, it's actually behaves like hydrogen. And then you say, well, what can have that amount of inventory? What can have that behavior? what can have that distribution, and what can emit 10.1 nanometer continuum radiation, cutoff continuum radiation, we're getting the same thing from our lab, from hydrogen. Astrophysicists is saying it has to be hydrogen in some unusual cold state. This isn't like in science. This isn't, you know, fringe literature, but mainstream astrophysicists are saying, based on the preponderance of evidence, that's what it is. So I'm just saying that there's an enormous body of evidence that would strongly support that the product of our reaction is in fact the identity of dark matter. But independently of that, we're making huge amounts of power, and it has a characteristic signature unknown in terms of emission that's not emitted by any known element or any known process. And we can identify the product by all these analytical techniques that definitively show we're making hydrogen in a new energy state. So, it answers some questions that are very, very profound in astrophysics, and independently we can confirm it on this planet, but it does give some reassurance that if there's something that's new and novel in terms of a new primary energy, you expect to see it in nature, especially something this energetic and involving hydrogen. In fact, it's ubiquitously observed in terms of radiation coming from the interstellar media, from stars, from white dwarfs, and from if it's identity of dark matter, it fits in terms of what we're producing in the lab and what evidence support the identity from astrophysical observations.
I know Mike's got 5 more questions, but maybe
Yeah, we can talk afterwards, and if you want, you can email me, and I'd love to follow up with you. So let me I got 2 last slides. So I want to introduce Dominic Jones. He's going to go over the 2 market strategy. Do you want to go right to the end? Before you get to the system design. So what you saw in there was the power source, and it's emitting this high energy light. We convert it into black body spectrum with the by it's being contained into a reaction chamber. It heats up the outer surface of the reaction chamber, which is carbon, to 3000 C, emits white light like a light bulb, and then converts it into electrical power. And then you can put it into a inverter. Again, this is industry product. There's companies like MSA that said they'd sell us as many inverters as we want. Doesn't seem to be any shortage. PV can ramp up very quickly. Doesn't seem like there'd be any once everything's up and made up to build up to capacity in terms of manufacturing capacity, which is estimated somewhere between 6 months and a year. There should be pretty much unlimited supply of PV components, light source components, inverters, and other components that we need to make this a commercial power source. Again, it is PV, so we could do inverter and then go to AC loads, or we can go direct DC, same output as PV, photovoltaic, and go to DC loads. And just to summarize, as I introduced Dominic Jones, who's going to go to market strategy. So we're reinventing electricity. It's a reinvent electrification, autonomous, completely off-grid. So it's mass-produced personal power. So once the manufacturing, like I was saying, somewhere between 6 months to a year to get the photovoltaic production equipment online, that's probably the rate limiting step. Then this should proliferate extraordinarily quickly, and especially because there's no regulation. We'll go on a flat per diem lease with no metering. Again, that would reduce or eliminate barriers to entry and bureaucracy in terms of quick deployment. And we could use cell redundancy. As I was saying, it's much cheaper to provide extra capacity than it is to use any grid connection at all, and that deleverages it from impediments from the grid and regulatory time delays. And then we're going to do behind meter temporarily, and then once we show reliability, then we're going to go completely off-grid and go to a global push in essentially all markets, starting with large kilowatt-hour capacity markets like commercial, industrial, working down all the way to residential. And then in the automotive space, we'll go after freight and buses and potentially car charging stations, and then ultimately down into individual automobiles. And it also has a very, very favorable application in marine and rail and ultimately in aviation. So in terms of all power markets. So I'm going to turn it over to Dominic, and then he's going to go over the go-to-market strategy.
We just have one quick question.
Yes.
As far as kind of next steps as we close this thing up and as we get these controls to monitor this, and are we controlling the flow at which the EMs are pumping the molten silver? What's the real trick to monitor to controlling it?
Well, we're looking at it now, and we have some fancy diagrams in terms of how you control the pump speed and then the ignition waveform, ignition current, and voltage and things like that, and the temperature profile. And right now, it looks like we may get to the point, as you saw in this last video, we may just have the computer just turn it on at a set pumping, a set, just keeping the level of control, but the average pumping speed would be pretty much constant. We keep it on a constant setting in terms of ignition system, and then ultimately shut it off. So it'd be startup. Like, you don't really care how fast your car turns over when you turn the starter mode. It's not tightly controlled at certain RPMs when it's in the ignition mode. And same here, the ignition they have a lot of flexibility in the range in terms of parameter space in which it will operate until it gets in that self-sustaining mode. And we turn all that off. We don't have to monitor it anymore. We don't have to control it. So control systems may get down to just controlling the hydrogen feed and then the cooling systems predominantly off the full tank.
Great. Thanks. Thanks, Randy. So I'm very conscious of your time, and it's 15 minutes or so left in this meeting. We started 5 minutes early, so I'm taking that. That's mine. So we'll aim to finish here quite quickly. My name's Dominic Jones. As you might have heard from Randy, I'm responsible for the business and commercial development within the company. I've been with the company about 4 months, and I've been responsible for putting the go-to-market strategy together to take the R&D effort that you saw and actually talk about how we're going to get it out into the world. So I'm going to just start by talking about the mission statement that we've generated, which is quite long by mission statement standards, but there's really a lot to do. First of all, we needed to build a generator which is an entirely new power source and bring that to market and ensure that it's safe, clean, and economical. That was very important as part of the process for us to be able to achieve the second milestone, which is this commercial launch process that we talked about in 2018. Now, what's very interesting about that is that the work really starts now for that to happen, and that's about identifying customers, early adopters, strategic partners that we can work with to go through the testing process to ensure that we have the thousands of hours ready for that commercial launch as we ramp up the system throughout the course of 2017. And Randy alluded to the timetable. We can talk more about that after this session if anyone has any questions. The third thing that we need to do is build what is really going to be one of the world's largest, as you pointed out, leasing, contract manufacturing and R&D companies. That's a mammoth task in itself. We look at the world, we talk about 30 countries or so that we think we want to do business in directly, and then build distributor partnerships for the remaining 166 or 165 if you're Chinese, because we don't recognize so on. And we need to get that done very quickly to be able to support what is obviously going to be a very big demand spike. Because we need to disrupt the legacy grid model, and we need to take this device and provide this economic, clean and safe power to all. And I'll talk a little bit more about that as we go through this presentation. And finally, and indirectly, we're going to solve some big challenges within the world, and some that, of course, are very near and dear to a number of the individuals here in this business, in this meeting room today. What's very interesting about that is, from a climate standpoint, and it's no longer an ecological fight; it's an economic fight. You know, we're able to bring a technology here that ultimately is powered by water, has no harmful byproducts that can revolutionize the way we consume power, and we can sell it cheaper than anything else that's out there today. So it really is kind of the silver bullet. So when we talk about that market, as Randy alluded to, it's an $8 trillion market. And that was 2013 numbers. Of course, it's continued to increase. Not only is it an $8 trillion market as far as the consumables and the energy that's consumed by the world, but it's actually about $1 trillion to keep it going. Certainly, when you look at the legacy grid infrastructure, there are a number of challenges, not only from actually the ability to be able to transmit, but the distribution element of that, and actually the security impact of having this very, very vulnerable, huge system that we're so reliant on. Having been in New York during the brownout, it was the most recent one. It was an interesting and somewhat fun time, but not something you want to go through on a daily basis. And of course, that energy is going to increase. That energy demand is increasing, predicted to grow by 56% between 2010 and 2040. That's very significant. And I think, as we'll talk about, that's with the current energy infrastructure available. We want to think about what we could do with clean economic energy. That would be very interesting. Renewables, whilst we've made tremendous advances, and a lot of that due to the efforts of a number of people in this room, in fact, really have only going to satisfy about 15% of that demand overall. That number varies slightly, but the challenges with renewable energy, certainly solar and wind, is that the sun is only available for a certain amount of the time of day, depending on where you live, and of course, depending on the season. I live in Florida, so I get more than most of you. But that's obviously a big challenge, and of course the wind needs to blow for there to be wind energy. When you look at electricity, which is a big and a natural focus area for us, largely because we have a generator that's really generating electricity, and as a result of generating electricity, there's a very simple replacement program. We don't have to develop, as we will as we move into the motive markets, in quite the same way. We need to deliver it on a skid, hook it up to the building that was once hooked up to the grid, and then move ahead. We are looking, and when you look at this $3.5 trillion that we're spending today, if we replaced everything, actually, based on the sun cell economics, it's going to be more like $1.5 trillion. Again, electricity itself is increasing, and we see a 28% growth between now and 2025. And actually, as we talked about, it's this obvious fit. It's about 42% of the energy value. It's about 38% of total energy use. Although actually, it's probably not the most prolific use of this technology. If we can get it into the motive markets, as I'll address just here in a second, that could be quite incredible, the impact that we can have. And as I say, whilst that's great, when you look at the launch of this technology, and I can compare it from work I've done in IoT, the Internet of Things, when you have cheap economic, reliable connectivity, it turns out we can connect more things. When you have cheap, reliable, safe power, turns out we can power more things. So what will that impact be? There's no study necessarily that can really support that level of growth yet. I talked about Motive. Motive is a great market for us. It's, as Randy alluded to, about 27% of energy use, but more interestingly, when you look at the number of cars on the road, there's 700 million or so cars that exist. Actually, they're really only using the power, this internal combustion engine we talked about 5% of the time. So, when you have a sun cell, if you can move it into a car, and you're driving it and using it 5% of the time, what do you do with the rest of the power that you're going to have that's always on? That's a really interesting opportunity. You take it home, plug it in. Probably already got a sun cell at home, so what are you going to do? I mean, there's a lot to think about in that regard, and a very interesting topic as we get to it. And we can move into that market very, very quickly once we address it, because there's 68 million cars produced every year. So, nearly 10% over 10 years, you could literally move from no sun cells in cars to almost all sun cells. That combined with autonomous driving technology could make for a very, very interesting world. Just food for thought. So, as I said, whilst all that's great, this market, this safe, reliable, accessible, clean power that we're bringing to the market is going to create a whole world of opportunity, and we can't predict that yet, but we know it's going to be good. So I'm just going to talk to you quickly about how we're taking this power to market. And for those of you that kindly attended our Industry Day presentation, this model will be familiar to you, which is good because we haven't changed it. So it was obviously reasonably good in the first place when we conceived it. This model just looks at obviously the core development. On the left-hand side here, you have the sun cell stationary markets. On the right-hand side, you have the Motive markets. And these are our routes to market. So we talk about direct lease, which is the Brilliant Light Power leasing co in whichever of the 30 or so countries we talked about. And then the distributor model. And I'm thankful today to be able to share some kind of pricing around that with you as well, which is the first time we've really shared that. And again, similarly, in some Motive applications, we will be able to lease the sun cells, but also we'll be working with development partners. In fact, we have already MOUs in place with development partners in that area to look at commercial vehicle development. So, phase one for us is an industrial and commercial launch. So, very simple market. It's a 150 kilowatt net generating unit. We are currently talking to organizations that sit within that industrial sector that use a lot of energy. We're talking to commercial organizations that use a little less than that, but still are significant customers. It means that we can build that one to few kind of commercial launch relationship for the first 24 months of our existence, and I'll go a bit more into detail on that here in a second. Second phase is residential, initially starting, and we may consider actually apartment buildings in that first phase should the demand be high enough, where we can deliver sun cells to residential. We actually have an industry advisory board. I don't know if any of you have followed that. We are about to make an announcement on that, by the way, so you will get to see that. On that industry advisory board, we have the expertise in microgrid, which is very, very helpful, so we can understand how we can address not only these very large areas, but also how we should look at these microgrid environments to serve more disparate single-family homes. And of course, commercial motive, which is the largest of the sectors, if you like, not necessarily by volume, but certainly by energy opportunity, and should be the most simple of the motive markets that we get to do. So that's sun cell powered trucks and those types of commercial vehicles. And then finally, looking at consumer automotive and the marine markets. Now, this is currently, as we sit here nearly at Christmas in 2016, the timing. Obviously, in any business that is at this stage of our evolution, there's a level of opportunity and opportunistic timing that may accelerate or change the priority of some of these things that we're doing today. But that's as it stands today. I would just say there's one other category. Again, I talked about this at our industry day, where we in fact had a number of these groups here, and that's development partners. We have a technology that can be incorporated into a number of different, obviously, applications, whether they be potentially space or military or heavy industry, that we're just not focused on. And actually, it breaks down slightly differently, not just to how we look at that from taking a sun cell and putting that in place, but there's also a process that sits behind that. If you if you look at, sorry, I'll go into that in a second, but if you look at that, there are a number of different other properties that may be very important to those, and I'll take you through that here in a second. So this is it. This is the launch pricing model for a direct lease customer of Brilliant Light Power. It's very simple for this commercial market. It's $90 a day. So if you use it for 12 hours, then you'll be getting the equivalent of a 5 cent per kilowatt hour rate. If you use it for 24 hours, which a number of the industrial companies that we're talking to will use all of that power if they're in metal smelting or some other area, you get to a 2.5 cent per kilowatt hour rate. We currently, through our planning process, at a reasonable volume, believe that we can get each individual installation of the sun cell down to about $2,000. Again, that's just the one-time installation fee. And that's it. It's that simple. It's a daily rate model. Makes it very easy for us to provision and bill, in fact. The other pricing model that I'll share with you today, and again, very important to understand here, is Brilliant Light Power is responsible for the installation, the certification, the insurance, the maintenance, albeit that through third parties, and of course the end customer management and billing. And we own the end customer relationship in this model. In the distributor model, actually, we will charge a minimum of $45 a day and set a price limit to the distributor that they cannot market the sun cell power for less than $90 a day. Yeah, so in effect, it's a 50-50 revenue split. In this model, of course, they're responsible for installation, certification, insurance, the maintenance, and the end customer management and billing, and they're just paying the royalty back to us. There are some other charges in this model that are very important to note. First of all, to ensure that distributors, and I can tell you, we are contacted by distributors on a global basis from the countries I have to get the atlas out and look for. You Google Maps nowadays, on a daily basis, so we've established a licensing fee for $5,000 per megawatt electric that we're charging to them up front to be the distributor. They obviously also have to be able to evidence their business plan to us and ensure that they're a real company, so there's a level of due diligence. That's the reason why that licensing fee exists. Secondly, we have this $75 per kilowatt electric fee. That is us, upon them ordering the units, what we charge them. So in effect, per sun cell, even though we own the sun cells, we're charging them up front $11,250 per sun cell that we deliver to them. Again, it's very important for us because there's plenty of opportunity and plenty of scope for them to work within this pricing model. We own and warrant each unit. We back those up with the manufacturer warranties and guarantees. Okay.
Just be on your website.
We'll be putting this out. Yeah. No need to write it down. So apart from distributors, as I said, we're working at the moment, and I promised you that I would finish right now, but we'll just be 1 minute. We're looking for strategic partners. We're evaluating these at the moment. These are early adopters of the sun cell. The strategic partner works with us through the field trial, through basically 2017. As a result, they get two things. First of all, access to the technology. And of course, secondly, they have the opportunity to strategically invest in the company. That's not for our working capital requirements. That's really for the project that we're doing with these strategic partners. And we are offering them equity as a return on that. And again, we have some structured funding rounds that we're working through that will form part of that engagement with these strategics. Anyway, in return for that as well, we also offer them discounts on the power. The other groups that we're looking for, I mentioned before, are these development partners. We have a number of these conversations going on at the moment. We have, as I said, a couple of MOUs as well with groups where we're looking at driving some of this development. As I mentioned before, there are some other properties that we talked about. So there's heat, there's light, there's the dihydrogen gas, which is actually, it turns out, an excellent helium substitute that can be used accordingly in this or as a result of the black light process or the hydrogen manufacturing process, and of course the power. So this is quite an interesting and illustrative model, and we ummed and ahed whether we would share it with you. We're going to take this off. This will not be on the web, but we internally have developed a target of about 10 gigawatts of pre-sold capacity before launch. Yeah. Now, assuming that with that 10 gigawatts is delivered 50% through the distributor model and 50% through the direct model, and which of course may vary, albeit that's how it looks stood here today. It's about, well, it's not about, it's 66,667 150 kilowatt units. We're building a manufacturing forecast to cope with that. We're talking to partners. We have RFIs going out to support that. Very, very important that we're able to manufacture at that capacity very, very quickly. We want to be able to deliver these orders within the first 24 months of our from commercial launch. It gets us about 25 million in distributor fees. There's about 67 million in installation fees that we are charging. Of course, the distributor will be charging those as well. That's the opportunity for a third party. And of course, about 375 million of equipment charges, which is the equivalent capital, or the equivalent charge that we're charging to the distributor for their charge. If we add all of that together, once we get to the end of it, I think the most important number is that we're already a 1.7 billion recurring revenue company. So that's after that 24 months. If you annualize that going forward, the numbers get very, very big in this game very, very quickly. You know, I've been paying my power bill, and I tell you, If you know, you know. So that's really an illustrative model of what we are, what we're targeting towards, and what certainly my group, as part of Randy's organisation, is focused on. So just finally, to leave this with you, albeit we haven't quite got the product to market yet, think of us as open for business. We are already taking orders. We have revenue. We will be driving revenue over the next year into 2017, and working with some early stage adopters that we really hope to change, actually, and really enable their businesses. So thanks very much for coming today, and I'm sorry that we ran 10 minutes over the allotted time, but I'll take any questions if you have time, absolutely. Yeah.
So, do you perceive there are any threats to your business model? In other words, like, basically the implications are trillions of dollars of economic value is going to rapidly shift. There's so many technological applications. Think of like the military applications, right? This could make obsolete so many military technologies. So this is a huge shift in terms of the direction of civilization. Do you think there could be, for example, people who say, hey, I don't want this to come out, or I want to stop this, or is there something else that could come along that would be a real threat?
Well, so to take there's two threats, right? I think the last one you just talked about, as in, quite frankly, we have been very, very public. We've pursued a patent strategy from a business standpoint. So Dr. Mills has filed pretty much, every patent in this field. In fact, as we mentioned before, there really are no other patent filings in this area relating to this technology. Of course, there are threats around whether or not someone might not want this to come out, but they're a little late, because we're all sat in this room, you all know about it. It's not like it's some secret lab, black project, right? You've written about it. A number of you have all been here. So I think that's not where the threats come from. The threats come from execution. It's really about being able to build a business, this leasing and contract manufacturing business, fast enough to be able to cope with demand, and to be able to run the right risk mitigation exercises around patent protections, around making sure that we look at the areas where this technology may be copied without permission, and we manage against that, and that we. Really, honestly, the most important thing for us is to have the right levels of finance available to be able to grow the business fast enough to be able to support that meteoric growth. But it's really about contract execution, but it's very, very simple. It's a very simple business. It's $90 a day, and it's an installer goes out, and we have a maintenance agreement in place. It's really, as far as business models are concerned, I used to work for, telecoms outsourcing contracts. It's very complicated. You don't want to go there. This is much, much easier. Yeah. Sure. Okay, so intellectual property-wise,
so you guys have intellectual property mostly related to energy applications. There are obviously a ton of other applications to this, right? Have you guys made any effort to file patents?
Actually, I just honestly, I'm not. You don't even want to go into it. We file patents on everything. Dr. Mills has filed. I don't even want to go into how many patents there are, because every time, it's very, very broad spectrum, very, very broad. And you're absolutely right. There are a ton of different applications, and we will be here very late. You can ask me the questions afterwards. I can probably answer some of them for you. Are there any other questions? Yeah.
The patent's been accepted by the patent.
Dependent on which ones you're talking about, because of course the inventions need to be there, but you're covered by provisional patent filing and etc. And again, there's plenty of patent attorneys in the room here. I'm not even going to go into that. So,
Technical question: what is the device working in the vacuum of space? Yes.
yeah.
It looks, it will revolutionize space travel. Right?
Yeah. Good. Well, thank you all for coming today, and great to meet you all, and that's very good. Thanks.